Angelo Rossi from the Jacobs University.
Thanks, Matteo. Thanks, everyone. I'm giving this talk on behalf of Andrea Nass. Andrea, she's a cartographer at the German Space Agency, and while I'm a geologist, and so is Alessandro, you will hear from him later in the afternoon. And basically, that's just to go back to the basics and look a bit of both the terms, the standards, and standards it can be, again, declinated in different ways, and the recommendation as well as use cases on how to map, particularly geologically, a planetary body. And doing this, of course, builds on something that Marco was already introducing, and we'll try to go a bit back to basics. As Matteo said, the polygons, the symbology is important, but even before that, there is a layer before, which Ricardo was mentioning. We need something to base our maps. We cannot just draw things, we need a base map. And this is seems to be obvious on Earth. We have Google Maps, we have everything since decades or centuries. For planets is a bit less obvious. Oops. So I'm quoting one person from Dr. Robida from the French Geological Survey, and I will give you access to the actual talk and information of him, but not without standards. So in effect, we do need standards. Maybe they are messy, maybe they are very basic, but we do need to agree on something when we map solar system bodies. And the first thing to actually start with is a map. And the map, that's the definition by a cartographer. By a geologist, probably you will hear something slightly different, but at the end of the day, it's an abstraction. It's something that it's a model, analog model or digital model of the reality, sometimes numerical model. It represents essentially a surface of Earth, of a certain planet, of a moon, and it doesn't have to represent all the surfaces. I mean, an image, it's actually a representation of what the surface looks like in optical or in radar wavelengths, but it can just be representative of certain specific characteristics. For example, topography, the contour lines, or just a color-coded hillshade. So a map is together a technical effort, a scientific or something instrumental to a scientific effort, and also an art effort. So all of these are together, and depending on the work that you do and on the side of the cartography, of course, you may touch more the technical or the artistic aspect. Nevertheless, a map is an abstraction and it's a model, and we should always keep it in mind, because when we see a map, it's not necessarily the reality, but it's a model of the reality, and that's also its own accuracy and errors. Of course, it does deliver communication, and it's important to communicate in a compact form, many information. Essentially, it's like dimensionality reduction. You put in a map, in a 2D image, many information, sometimes, particularly with geology, also 3D. So as Andrea mentioned, you distill. So you're making some distillation of reality, of data, in order to be conveyed in a single medium. The single medium in the old days was analogic, was print, and nowadays it's all digital. So of course, the possibility are increasing. But at the end of the day, this applies in the very same way to Earth or to any solar system body. Why do you map? Well, you can map for many reasons. Obviously, Matteo was mentioning from the slide one, you map to know the resources and to understand what's below your feet. But when you do it on planets, you can use that aim, but you may just want to map a surface to be sure that when you land there, you don't crash, and you don't crash 3 billion of spacecraft. So there are technical engineering aims, typically for mission planning. For the Apollo missions, there was a lot of mapping before sending people or even robots in the precursory mission. You may also want to figure out the safety of individual landing site, but also the possibility of trafficability, how to move around. So basically, you also do it to give a context, because whenever you are there, you have a very focused view, but you need, as Ricardo was putting at the base of his pyramid, you need contextual pre-existing information. That's why mapping is so important, even before it becomes geologic mapping. And of course, you have the scientific task linked to mapping, which can be fundamental or applied research. And you do start with the reconstructing the image aspect, the albedo or the optical aspect, the topography, more or less directly, as you've learned. And more what's coming on the surface, remember the talk of Matteo and Marco, and the stratigraphy, so which is the series of events that occurred on a certain area. So with all of this, you can start constructing thematic maps. And one special case of thematic maps that you have seen exemplified on Earth many times in the past half an hour are geologic maps. So in this respect, planetary mapping can get different meanings. If you talk to people that are doing spacecraft planning, mapping is essentially planning the observation to get an image. If you talk to people that are working on geospatial data analysis and geomatics, that the mapping is doing photogrammetry or stereogrammetry, or essentially image co-registration and geodetic registration, control networks, mosaics, and so on and so forth. And of course, planetary cartography, which embeds also geologic cartography, it's the technical and artistic creation of maps, which comes together. And you saw it from the case of the print setup on Earth. Now, how do these different meanings get together? Well, essentially they are incremental and they are sequential. So before even thinking of seeing something on an image, you have to send a spacecraft. So you have to plan. Before taking a picture, you have to plan the observation. Once you take the picture, you do need to get the telemetry down to actually do all the data reduction that for astronomers and planetary scientists is more or less very similar. So astronomers and astrophysics will know this already very well. And once you do this, what is called in astronomical world reduction is mostly called processing for geospatial data. Essentially, it's radiometric calibration, geometric calibration, co-registration, mosaicing, and so on and so forth. And then what, as a geometric person, you call an end result, in fact, for geology, is the beginning of the path. So you do get your image, you arrive to a digital image mosaic, and that's actually, it's a base map. So that's the layer that we put below, one or several layers, in order to allow us to do exactly the exercise that Ricardo was showing. So produce geomorphic or geologic mapping. And there are many limits to that. You remember that Marco was mentioning samples and drill holes. All of this, it's extremely challenging, if not impossible in many solar system settings. Plus, the object that you make, they have a very wide range of size, of gravity, of homogeneity, geological diversity, and so on and so forth. As a rule of thumb, the bigger they are, the more complex they are. But sometimes, even remarkably small objects, they have quite a complexity. And the work of the groups, including Matteo and Luca, on small bodies show that actually even very small bodies of 2 or 3 kilometers can have a rich geological complexity. How do we capture it? Well, we can capture it from orbit or even from the surface. And this gives a different perspective to mapping. You look at things from an orbital point of view, and you can do more or less the remote sensing work that has been exemplified by Ricardo. And the more you get close to the surface with platform that can be a rover, that can be lander, can be hoppers, or any sort of dogs running or zoomorphic robots of the future, they will be able to collect data useful for geologic mapping. And their integration is indeed an issue. The base map also do evolve with time. Before the Apollo, of just a couple of years of difference, so improvements on the base map. So as much as the geologists say, you can survey as much as you know, so you survey more or less your culture, your geological culture, your base map, the accuracy of your map is as good as your base map is. So both the skills, the knowledge, the data, as well as the maps, the base maps are important to get geologic maps going. How do you integrate them? You will hear more on this afternoon, but essentially you have to integrate your data. And this is typically the task of cartography, and nowadays the task of geographic information systems, GIS, digital mapping, geospatial database, spatial infrastructure, you name it. There are many names, but at the end of the day, is having some set of standards to put the maps together and some set of tools to be able to get the data and look at them in an integrated fashion. In this respect, the approach, the very classic and old school approach of geology, which is essentially stratigraphic, can be applied to modern technology. And this is more or less the gist of the school, to use quite common sense aspect tools with data and with more or less high tech or kind of modern integration tools and techniques to be able to apply them. But at the end of the day, they're not that much different. So if you just look at the planetary side, in the 60s, the first geologic map that Matteo was showing was actually performed on telescopic images of the moon from Earth. And from there to the late 2010s, or now essentially, we moved more and more towards spacecraft-based base map. But the concepts are the same, and what evolved a lot are the tools, the quality of the data sets, the accuracy, as well as the quality of the additional data that were not present back then. For example, compositional information on the moon. In those days, back then, data were essentially collected. They were used by expert mappers, interpreting them. So a geologic map tends to be as much as possible free from interpretation, but there is some interpretation. And that has to be something that has to be transparent, because when I call something a basalt, I do interpret something. If I don't have the model mineralogy, I cannot say it. But for different level of inductions, one can say it, for example, on the moon with contextual information, sample, and so on and so forth. But at the end of the day, the product was one. And the end users can be agencies, can be scientists, can be libraries, can be whoever. Nowadays, in the digital domain, things, as Marco was showing, are much richer. One has essentially GIS files, geospatial data databases, and these databases can be queried. So it's not only a kind of a bidimensional map and a single product, but it's a rich set of products. And this can be not only used as such, as integrated database, but also individually. They can be reused, they can be improved, which means that it's a much more dynamic and interactive mapping process that can be at the scale of the days, the weeks, the months, but also the decades. Now, when it comes to method and standards, of course, we need this kind of distilled representation of reality to be easy to access. We need data to be comparable. If I take a picture and I take topography and I don't know how they correlate to each other because they're not using the same spatial reference, obviously I cannot use them effectively, and not to mention geologic mapping. And of course, the old maps, being analog, being digital, they should be reusable. So actually the information can evolve and the interpretation can be based on an improved set of data. So when it comes to methods of interpretation, part you have seen, part you will see during the week. Data and data formats, you will mostly see them this afternoon. Software tools, same during the week. When it comes to map creation and design, we will get to it in the next few minutes. First of all and foremost, most important, the coordinate reference system on Earth, it's relatively well settled, although it's an entire set of, it's an entire discipline, the geodesy. On planets, it's much more complex to some extent and much simpler in another, because obviously there are many reference systems. If I get to Mars, I have to get to Mars. So I have to navigate, and I have a reference frame, for example, centered on the sun, on the barycenter of the solar system. If I go there, then I start orbiting, it doesn't make sense to use the same reference frame. So I have to use Mars, and I have to use a certain Martian reference frame. Once I look at the surface, it doesn't make sense to use the center of the planet and the solid angle. It makes sense to use a map projection, like the one that you see on the right. This seems simple, it is not. And of course, many trade-offs needs to be made. Also, when it comes to the shape of the body, once I orbit, it's not so obvious. I mean, I can approximate any planet to a sphere, but in some cases it's not enough. I can approximate to a biaxial or triaxial ellipsoid, sometimes it's not enough. When I go to a comet or an asteroid, I can't. But the good news for the next days is that for most planets and moons, the first order approximation of the shape of a body is essentially a biaxial ellipsoid or a sphere. When it comes to putting the maps into a layout that is similar to the one that you have seen, of course, there are different ways to do it. And this also depends on what you want to show, because not all maps are similar and not all maps are respecting reality. Remember, they're a model of the surface geometry. For example, I can have a map like Google Maps that shows everything that looks pretty good in shape, but then it ends up that Greenland is as big as Africa or South America. So this is a problem if I measure the areas in that projection. So there is references I will point to at the end of the talk, but essentially map tiling systems are done to minimize distortion or to maximize essentially the effectiveness of the map for a certain latitude, longitude, latitude range, size of the map, because if it's global or if it's local, and also depending on what I look at. If I want to see the angles between the folds properly, definitely I need to choose a map projection that does respect this. Plus, I need a legend, and both Matteo and Marco were showing a lot of it. A legend can be a set of symbols that are, again, standardized, a set of colors that are giving you a visual impact. And this is an example of the global map of Mars, that has been done by USGS in the last few years, has been updated. So you see on the right, the map, you see also that the scale varies with the latitude. And this is also important. And then you can see on an excerpt, actually a cut at the center of the stratigraphic framework in the area, which means that, for example, the Hesperian units, they are older than the Amazonian one, as you will learn more and more on Wednesday. To do this, Marco was showing already, you do need to have certain standard of which are the fields you map and how you correlate them. This can be as simple as we will do in the course of the talk, as having a name of a unit, a type of structure, limited a type of contact which is maybe sharp or is not sharp, but it can go a very long way in terms of complexity. And this complexity has to come hand in hand with standards, because if you have complexity without standards, obviously my map will never be interoperable or even understandable by you, and vice versa. That's why this is so important, and that's why also GMAP will try to make this, following the example of decades on Earth, to make it, and also on the planetary side, to make this as standardized as possible. Then there's another point, which during the discussion, maybe Ale can deepen more, which is how you license maps. You saw that a lot of these things are available on the internet. You get them, you use them. You can actually print T-shirt like H&M does with the NASA logo because it's public domain. So all fine. But when it comes to data, sometimes you also see that the maps are available in a print format, but you never would be able to get the digital GIS files, and you need them for your work. So all of this is because there are different levels of licenses. So when it comes to reuse of data, it's important that there are clearly licenses that are respecting the intellectual properties, but also that are allowing, for example, reuse, spreading of maps, encouraging additional science, which at the end of the day will be more value from the invested public, typically money. So some example to close the overview on actually mapping projects, because a mapping project is something which is bigger than a single map. A single map, I can do it. A mapping project typically needs some institution, some kind of group, and several individuals or several institutions. This can be scaled quite a lot. Some of them, they are institutional. For example, the USGS planetary mapping projects are funded by NASA, and USGS is chartered, and they are going on since the Apollo times. Some of them, they can be very specific to a mission. For example, the DOME mission to Ceres and Vesta, or the Cassini mission, or the Bepi Colombo mission, they do have a specific mission-related planetary projects. Or they can be just science or exploration or resource utilization individual projects, like a single map sheet. For example, there is a PhD student, anyone, working on an area, you make a map, you want to publish it. That's where GMAP comes in fact, and with Matteo, we will discuss it later on in the week. Example from the US mapping program, there are many bodies. These are just 2 or 3 examples on the global map of Mars that has been released a few years ago. the Mercury quadrants that are part of the global the USGS program, as well as the merging of existing maps of the moon into a unified effort, which is also something that has been done by USGS in the last few years. And that's exactly similar to what Marco was showing. When you put together the different sheets of the Italian map into a single one, you do have to homogenize. You really have to make sure that the units are fitting. And that's very tricky on Earth, because maybe in Italy you have a map that has been collected in the 70s or in the 50s or in the 30s, and another one in the early 2000s. So this homogenization does need a lot of effort. In this case, it was not so, not as tough as on Earth, but still different people around the dwarf planet Ceres worked on different map sheets, and this map sheet had to be put together. You will have later in the week also possibility to discuss it with Andrea, because she was overseeing this. But from this to this, it took quite some work. And remember that Ceres is not as complex as Earth or Mars, but still. So this is an example of how a mapping program related to a mission can actually produce quite a lot of geological work. Or you can have single map sheets parts of a project, in this case, the PlanMap projects that has been funded by the European Commission. And you have one case on Mercury, you will hear more from Dave and Jack, and one case from Mars. You will hear from both of them. But these are single sheets, and they do have elements of legends, of static cross-section, an image, and some additional information, stratigraphic framework, and so on and so forth. And metadata, which everyone knows are data about data, are also something important. In this case, they're not as standardized yet, but essentially the map-wide metadata, or someone was mentioning in the question before, the data about the incidence angle for each image, all these metadata are of key importance. And even an individual map taken as a single data granule does have certain metadata that are essentially usable for data discovery. So you want to look for a map that has been done in a certain bounding box of crowd latitude, then actually you can find it. That's why metadata are so important in this kind of geospatial data. And again, single map sheet, you find it. I just took some examples from recent and less recent maps. They can be anywhere as long as they have a base map. Of course, they have some kind of process behind producing the map, but essentially there is not really limits of the size of the location. And again, these are kind of it's like a grassroots geologic mapping. Well, not all of them, but most of them. Now, I want to not close, but give you a couple of slides that I show you here, and you will have access to this on the later in the day or tonight on the web, because there are several resources that are freely accessible. There is also one paper from Andrea that you will find also available there. Some other are linked. If you have issues to find them, get in touch with us. There are some references that can help. The last one is one seminal book of Ronald Greeley on planetary mapping, and there is a lot of resources online. Just if you look at the USGS mapping standards and guideline, the PlanMap one, the GMAP one, there's a lot of reference and things that can help you going ahead. There is also previous workshop, maybe some of them, they are less of a kind of a school type, but there is a lot of accessible information, particularly the introductory talks. So I really invite you, apart from looking at the slide, looking at the books, at the paper, have a look at these resources, because they're there, they're available, and I think they will help you getting started or getting moving ahead with your mapping project, which I hope you will be able to perform in the next few years. Having said that, we're approaching the half an hour scheduled, and now we can maybe collect the question and the discussion for both Marco and Andrea's talk and discuss it together.
Well, thank you, Angelo. So we are open for questions. We have at least 10, 15 minutes for questions. You can do them either by writing in the chat or intervening, raising your hand.
And if you have them later, you can always put them on the forum.
Yeah. So no questions at the moment. Probably you will have them when you will try to decide the symbol and the legend, and
Yes.
And understand the projections of into a reference frame.
Yes, because of course now everything seems that everything fits, everything is nicely colored and symbolized, but you will see the things then in practice they're getting a bit trickier, but also funnier, so to say.
Hello, my name is Camilla. I work at the Unibern Physical-ish Institute. And I have a very quite specific question, but I guess it will be also answered during the practicals. But if you have several observations at different latitudes, is it easy to have some sort of global map without a specific projection, so you can move to these different observations without having to switch from one projection to the other?
Okay, that's a good question, in fact. And in fact, it's not that you don't need a projection, you just need a global projection. For example, can you see my screen still or not? I think I have to share it.
No, you don't see it.
One second. Can you see my screen?
Yes.
So basically, this, if, for example, you look at this, these are different map quadrants. The two round ones are like stereographic projections, so north and south. Then these things that are looking a bit like a trapezoid with a curve, they are kind of mid-latitude, they are conical projection. And the one that are looking like rectangle, they are cylindrical. So if you want to use just map a certain part, you can use different projection. If you want to use map the whole thing, you can choose one of many projection that can map the whole thing at the same time. So you can have, for example, a cylindrical projection that maps everything, and you can have a mole-wide, you can have many of them. I can point you to some resources here. For example, there is the book that has, I think, many of them, but essentially it's fine to use one single projection for all your observation. You just be aware that you have to make sure that the sizes or the angles or the shapes or the distances are or are not respected. But for having a kind of a synoptic view, it's perfectly fine to choose a global projection.
Okay. Yes, because so I work mainly in the pole of Mars, the South Pole. But I do have observation that goes beyond the polar stereographic projection.
Until which latitude?
Until 50.
But you know that, I mean, you can also extend the polar stereographic until 40 if you like.
Oh,
so yeah, I mean, it's not a problem. If you want, you can just make it bigger. Of course, the geometry, as long as you're not going below the equator, you should be good with it. And then, of course, the scale won't be very correct, but you can still see them in a kind of a contextual view.
Yes, okay.
So that's fine. In fact, I would suggest to keep the stereographic or something azimuthal or some sort.
Yes, that's what I've been using so far, but it sometimes distorts my observation that I have to manually put back into place. But if there was a more global projection, like, so I have a few base maps that are available pretty easily online. And what I wanted to do at the beginning was to have just some sort of globe projection.
Like an orthographic projection, you can see something from like looking at the moon.
Yes.
Yeah, these are all doable. And in fact, I don't know if we have time to tinker with that too much in the week, but there are resources and with standard open source tool and libraries and the things you will learn this afternoon, you are able to make your own base map. If you have some data, you can do mix and match, change the projection and choose the one that fits your needs.
Yeah, that's what I'm hoping from this workshop.
Yeah, hopefully you should get it out of the workshop.
Yes. Thank you for your answer.
Yeah, welcome. Anything else?
Seems not in the chat at the moment. Yes. There are questions about the integration and combination between DTM and stereo images. So how can this can be done? Actually, stereo images are used for creating DTMs.
Yeah.
And afterward, you can overlap your images on your DTM. So this can be easily done. Some of the activity that we will do in the next day will be even to show this kind of overlapping and perspective views like the ones that Ricardo has shown you before.
Yeah.
I actually, even if I am coordinating, I have a question. Can I ask the question to Marco?
Marco,
is he listening us?
Here I am.
Okay. So how many people are involved to make a kind of synthetic map like a national one on Italy that you have shown us?
Do you mean the synthetic one? Or do you mean the 1 million?
Yeah.
Oh, we worked in more or less 8 geologists and 2 or 3 cartographers.
Okay. So
because we analyzed all the previous publications and maps and so on, and so we divided the complete coverage in 5 or 6 different areas, and so I follow the North Italian, or other people follow the central one, or Sicily, or so on, and so we were 6 or 7 people, geologists.
Just to integrate the map that were already there, isn't it? Only I would say it's an hard effort, but integrating them, you have needed 11 people more or less.
Yes, more or less, yeah.
Because for a single sheet, you normally have even more people for a single sheet of 1 to 50,000 scale, isn't it? Yeah. So if you see, it's quite big effort to do this kind. So another things they ask me is how long did it take for the national one? I think.
Okay.
And even I would say for a single sheet.
Okay, for a single sheet in 50,000, it is different from the original knowledge. If you have some data collected before, you can do it more quick. But the program is 3 or 4 years for a geological survey. And in the meantime, the preparation of the database and so on. And so the project is 3 years for each geological sheet. It is not respected everywhere, because in some cases some people go longer than this, and so they realize the shit in 5 or 6 or even 7 or 8 years. But it depends also for bureaucratic reasons. While for the realization of the geological map of Italy at 1 million that we presented in the 32nd International Geological Congress in Florence in 2004, we worked for 2 years.
So we can say that for a single sheet of 1 to 50,000, you have 3 or 4 years of 10 people working on that, at least, even 15, and other 10 people for other 2 years for making the synthetic part. I would say that for planetary geological maps, so it will take normally less for a sheet to be done, but in any case, it's quite a long time. You, in any case, during this school, you will map a very small areas, so you will be able to finalize your maps even without taking even in 1 week. Okay.
Yeah. You have to take in account that in the sheet in which there is the marine area, there are no more many data, and so you have to collect new information from this. And so this is because marine geology is a new method of representation. In the past, we have not the marine geology on the previous series. The marine geology were not represented.
So there is also another questions that you have, Angelo, already answered in the chat, but it was about asteroid mission with multiple instruments and no cartographic information. So the problem is how to define the projection system for a new body in asteroid mission to small bodies. Let's see, as far as I have we had experience on the comet. Actually, we used the instruments and capabilities of making a shape model of the comet, and we afterward defined some references on the surface to make a relationship for indicating the latitudes and longitudes. So we had a reference meridian. In that case, it was a bilobate shape body, so it was quite difficult to do it because it's quite complex things, and to make a real projection that do not deform too much the two bodies together. But normally, when you go in a new body, you use the instruments for creating as fast as possible a reference system, and into which you can afterward map. You can even go in parallel. You can start interpreting the images without a reference at the moment, and then you can build up your reference afterwards. So another question is about DTMs. So I'm not sure to have understood the question, but the point is for stereo pictures, if how much is the work for creating DTMs on stereo pictures of tiny things, should they do the DTM? Should they be created automatically, or how much intervene of the manual intervene should be done?
Matteo, Tatiana, Riccardo, I think can comment on that, on this.
So basically, there are different ways to do that. We want to go in detail because it's a very complicated matter, but line of principle, there is this software by USGS, it's called ISIS, and as that is used to calibrate and ingest all the raw data from satellites, and from that you go to some stereo pipelines. There is one open to everybody from NASA Ames. Basically is able to ingest the stereo images and detect type points between two images, so different features with different levels of observations, and derive in the end stereo DTM. It's not totally automatic, but can be automatized, but it differs from planet to planet and from instrument to instrument. Manual intervention may be helpful in some cases, as you are required to put, let's say, ground control points of homologous features in different images. Just, for example, if you are working on very, very high detail images, you might want to not rely only on the automatic type points that are generated by the software, but also add some control points by yourself in order to increase accuracy. You have to take in mind, of course, that after then the DTM is produced, the resolution of the DTM is usually 3 times larger than the image's original resolution. So if you have an image that is 1 meter per pixel, the DTM is at least 3 meters or 4 meters per pixel. This is also because you have to take into account some instrumental noise or some interpolation noise created by the software itself, that when it puts together the 2 images to create the 3-dimensional surface. Then if you want to create a super high fidelity DTM, there is also a technique called shape from shading that is taking also into account the illumination conditions, that of course creating shadows and lights, and so defining the morphology in order to refine the DTM. But above a certain threshold of resolution, of high resolution, you cannot expect, for example, to have a small boulder like in 3D, like a DTM, if you have an image which not so high resolution. Then the stereo images, 1 or the 2, can be auto-rectified, so rectified on top of the DTM, so it's deformed according to the 3D surface in order to be exactly projected onto that surface in order to take into account the deformation by the topography. It's not entirely automatic, it needs some tweaking, but there are plenty of documentation to do that. It's not in the aim of this course, because also DTMs are provided by instrument teams sometimes, and also there are repositories for DTMs. But if you wanted to create a specific one on a specific location that is not covered, you might want to proceed yourself, and this is a totally different story that requires a bit of training experience and also computational power.